to smart materials and surfaces. Today we're going to talk about analytical techniques, so how we can use materials to measure things. So the first thing that we want to think about is a quartz crystal microbalance, which is just one technique. It's one of a family of techniques where we measure the mass of things on a surface using an acoustic wave. So first of all, let's look at what's going on. The quartz crystal is what you would have in your computer or in your watch, and it's vibrating, it's oscillating under an electrical circuit, but the quartz crystal is determining the frequency. So it has a very sharp frequency resonance, and it's using that, or the clock in your computer or in your watch is using that to keep time. And it does that because of piezoelectricity, which I'll have to draw. So here it is. This is a piezoelectric crystal, and it's set up so that when we apply a voltage to it, the surfaces move relative to each other, which is known as thickness shear mode. So it's shearing in this direction compared to the bottom. And this one is completely unfixed, so that both the top and the bottom can move, which is the easiest way to set them up. Then we apply a voltage to it, and it causes it to shift. When it shifts, nothing interesting happens, or something very interesting happens. It moves, but it's not oscillating. We can't measure anything. If we vary the frequency, we can find resonant frequencies where exactly one wave, or in this case half a wave of the acoustic wave, fits into the thickness of the crystal. I've not considered the thickness of the metal, but that will also be affected in here. If the quartz oscillates at this frequency, it will be able to couple particularly well with the field, because when it's moving back of its own accord, because it's oscillating back, we will be powering it as well. The AC will have switched to the right direction to be pushing it. If we're obviously close to it but not quite, then we'll have a problem, because if our AC is slower, then it will start to come back while we're still pushing it in this direction. And if it's faster, then we'll try to come back, but it's still wanting to move further because it's carrying on moving, so we're actually powering against its momentum. So there are frequencies where this will oscillate better, the resonant frequencies, and that's what we're trying to find with our watch. We're trying to find a resonant frequency that we can then measure. So we set this up, this AC up, to be a frequency close to the resonant frequency, but not very well defined, which is quite easy with normal electronic components, because they have tolerances, they have variations, so they're not super sharp. Tolerances is a bad name for it. So they have a wider band of resonance than the quartz, and the quartz narrows the band and fixes it to what it wants to do. Quartz, in this case, as a piezoelectric material and as a resonator, is particularly good at fixing the resonance, which is why we use it in watches and computers to determine the time. Also in many other cases where we want a time signal. Okay, so now we put an extra layer of something else on the top of our crystal, and it behaves to a first approximation just like extra quartz. So we've made our piezoelectric material a little bit thicker, and so that makes our middle move up. It shouldn't have increased in amplitude. Let me not do that. But it's made the wavelength longer. So we've increased the wavelength, which means the frequency goes down because the speed of sound doesn't change in the material. And so we can detect when something is adhering to the surface by a change in frequency at the resonance point. So that's what we're trying to do. A simpler method of doing that is a cantilever, which is a little bit easier for us to understand because it doesn't have any piezoelectricity, making it more complicated. So if we take something like this is a cantilever. We have to make it out of something very small, like a piece of silicon wafer. It's very thin, and it's like a ruler hanging off the edge of a table. If you flick it, so if you play it, it oscillates, it will vibrate at a certain frequency, and if we can measure that frequency, we can determine some things about the properties of the ruler, which is the stiffness and the weight distribution. If it's just one material, so it's distributed all over it, then it will behave as if it's just the weight that is doing it. So if we make it perfectly, we make a perfect cantilever and we add material to it all over, then it will start to oscillate slower because it's heavier. We have to hold it by a very massive or very stiff clamp here on the end, or however we're going to hold it. Usually they're micro machined out of a single piece of silicon so that they can then oscillate. We also have to be able to excite it some way, which isn't so easy. Some of the ways would be having two different materials on here and then heating and cooling it, or applying a voltage or something, and then we need to be able to read what frequency it's oscillating at. So the advantage in understanding goes away a little bit in the complexity of how it works and how we're going to measure from it. The next thing that I would like to think about is if we have an optical fiber, for example, and we pass some light down it. The light doesn't pour down there like it's a tube. It's bouncing off the inside faces at different angles. So we don't couple the light in perfectly parallel. Some of it is bouncing at a steeper angle and some of it is going almost perfectly down the center. And it will depend a lot on how smooth the outside is and whether it's bent into curves, how much the light interacts with the sides, and whether the light that interacts with the sides is always the same light. How does it do that? It's a total internal reflection at this point. So the light is reflected off the inside face of the fiber where the refractive index is changing very much. But what happens if we now do something with that optical fiber? What happens if we put it in some water, for example? If we put it in water, the optical density difference, the refractive index difference between the glass or plastic and the water is much lower than it was between the glass or plastic and air or nothing. And that means that a lot more of the light can escape effectively. So if we take an optical fiber and we pass light down it and we measure the amount of light that comes out the other end, we can detect, because of the amount of light that is lost, we can detect the refractive index to a certain extent of what's going on outside. But more importantly, it's not just the refractive index of what's going outside because of what's going on really here. So how does the light decide? It's quantum mechanics, so it sort of decides. How does the light decide whether it's going to escape? So it will be refracted towards, so it will be refracted towards the normal, whatever that one's called, if it escapes. So it's going to go out at a steeper angle. If it is reflected, it stays inside. So it can do those two things. The light has to decide at this point whether it's going to do that, and it needs to know what the refractive index is outside. It can't do that by magic. So quantum mechanically, what that means is the light wave peaks out very little outside. So if we have a look at the wave, when it comes to the here, it is reflected, but it's also refracted at the same time, which means at some point, some of the energy is coming out and some of the energy is going in, and then it decides to reflect and goes back down here. So even if it reflects, it has detected something about what's going on outside, And that is how our ATR infrared attachment works. It bounces the infrared light on the inside of a piece of zinc selenide. It can't be glass because glass is not transparent in infrared. And the infrared beam looks out a little bit. It's a fraction of a wavelength, so it's not very far. It looks out a little bit into the outside world while it is doing effectively the maths of working out whether it should be bouncing off or not. And if we set it up right, so it's close to escaping, but not close enough that it can escape if we just put water on the top, it will bounce back, but it will also interact with the outside world. So in that case, it's a very practical solution because we can put the things we want to measure on the outside here, and we can measure them even though the light technically never leaves the central material. If we do this with optical fibers, we can insert them into other materials and we can measure things. So what we can measure is the refractive index of outside, because that will determine how much escapes depending on wavelength. So if we send white light on there, we'll lose some. If we attach a molecule on there that could absorb one of the colors of the light, then some of the light will get lost. So the light that goes in will come out with missing some components which were absorbed here at this point where it bounced off. That's good in this system because we could then take the optical fibers and put them into something, coat them with a chemical that changes color to some stimulus that we want, and then we can detect a change in color or a change in some property by a change in the color of the light. Even better, we could theoretically get some information as to where it is, because we don't have to put the same color on the whole length of our fiber. So we could insert a fiber and we can measure different things at different points on it. But that also, just as the same as the quartz crystal microbalance, it has requirements for what are we going to put onto the surface to measure things. How are we going to get the thing that we want to do the measurement? So we need a material that will do something smart then. This is partially smart because we've made a smart material, but we still need to add a component to measure the thing that we need to measure, whatever that is. The third theme that I wanted to introduce today was electrochemistry, where we have, I forgot to draw this, so where we have a liquid in a container, we have an electrode inside the container, and we want to apply a voltage to it to make things happen. If we have something in there that can be oxidized or reduced, so we'll put something simple in there, let's have H+. H+ can go to, it's a bit reversible, go to H2, which is a gas and can escape. We need 2H+, and obviously we need 2 electrons to do that, which we can have off our electrode if we make it negative. But for the purposes of completing an electric circuit, we need another electrode over here. I've drawn that as being really big so that we don't run into the difficulty of limiting the current by the surface area of this electrode. I want to concentrate on this one. It's not easy to do this. We need a third electrode usually to make the system work, but for the purposes of explaining it, we'll start with 2. If we make this negative, then at some point we will activate this hydrogen going to, or hydrogen ions going to hydrogen gas, so we can start making hydrogen. And the amount of hydrogen that we can make per unit time, the current that we get, is dependent on how much hydrogen is in solution. So if we have H+ in solution, it can only get the electrode at a certain rate, and the more acidic the solution is, the more H+ there is in solution, and so the faster we can do it, which means if we turn our voltage up and up and up, we will get a current that is limited by the amount of H+ in solution. If it's water, then it's very high, and so we will end up having difficulty measuring the current. But if it's not water, for example, and we want to measure H+, then we can measure it very accurately. If we want to measure something else that has a lower, it's easier to do than hydrogen. So maybe, what can we have? Maybe we want to oxidize some organic chemical like citric acid or acetic acid. Then we can oxidize them up. So we take electrons off. No, we're giving electrons to them, sorry. Again, if we oxidize them, no, hang on. Start again. We take electrons off them. Oxidation is loss of electrons, so it is the other way around. I wanted one that was the other way around. We take electrons off them, so we make this positive. We can take electrons off them, then we can measure that too. What would we do to make a sensor with any of these devices? Let's start thinking about that with a specific case, and that would be antibodies or antibody linked enzymes. Okay, so this is my antibody. It looks very much like our Hochschul-Rheinwahl symbol of the two rivers coming together, but in this case it's a chemical that's made by the body or bodies of animals, because all animals have them. And I've just changed colour. It has two sticky ends. The third end is signals to other body chemicals. It has two sticky ends that stick to things, including things like coronavirus, for example. So if we have an antibody to a virus, the virus will tend to stick on here. Oh, my pen's run out. The virus will tend to stick on here. I'm going to have to give up and make it blue. The virus will tend to stick on the end here, and it will sometimes, or very often, capture two. The antibody will then signal to other things, and that will help the body to defend against whatever it is, in this case a virus. But what happens if we want to use it for sensing? We want to detect a virus using an antibody. So first of all, we need to make one. Let us assume we can make one and purify it. Finding out how to do that is a job for a different day. Once we've done that, we can take our antibody on a surface, and we can take our antibody, and if we can attach it to a surface, so there's another problem for you to think about. How are we going to do that? We can attach it to a surface. If this surface is a cantilever or a quartz crystal microbalance, something that works in a liquid, which is a problem for both of them, because if we have a cantilever and it's bouncing up and down, that's difficult because it will be held back by the viscous resistance of the water. If we have a quartz crystal microbalance, then it will be measuring the water on it as well as whatever we want to apply. So there are problems. It makes everything much more difficult, but ideally we would put our sample onto, so a sample of blood or whatever it is, onto a surface that contains these antibodies and the sensing element below, because we need to make it smart, and then it will detect by attaching some of the viruses or whatever we want to detect, and then we can measure it using the change in properties. And we could do it with any of the things that we've had so far, which was a quartz crystal microbalance. Cantilever is a little bit more difficult in this case because it loses a lot of energy to the water. A glass fiber, where the density change close to the surface will affect the amount of light that is lost. And it's a little bit more difficult than that. We need to organize it properly, but also we could do some electrochemistry, although it's not quite as easy as that. The problem with electrochemistry is, if this is an electrode, so this is a metal down here, let's make it platinum, PT, so that it's not doing anything, because if it was copper or something, it might just dissolving. So we our platinum electrode is waiting for something to come along that can react with it, then we can measure current. So we need to make something that wasn't there before in response to our virus attaching. So now we need another thing. So we need another toy, and in that case it would be another one of these antibodies. Oop. Let's have it sticking out there. And this other antibody will have something else attached to it, which will be an enzyme that generates chemicals that we can detect at our electrode. This is how glucose detectors are made, for example. If we want to measure glucose and have a sort of electrical signal, we can do it by having a glucose oxidase, so an enzyme that oxidizes glucose, and we can use that to transfer electrons to and from our electrode, and then we can measure the current from that, which will tell us something about the amount of glucose. In that case, we wouldn't need the antibody. We would just need, if we want to measure the glucose, we would just need to attach the enzyme to the surface. If we want to measure so a virus, an antigen, then we would have to attach the enzyme here to a second antibody, which is very much like a further system which just uses light to do that, but we're interested in the materials. What I'm interested in is how do we, for the purposes of the course, is how do we attach these to the surface, how are we going to make a material that does something smart, and the idea of the course is that you choose some of these and you investigate it further yourselves. So that's only a taster of all of these things. We need to go into them all in more detail. But first of all, I need to know how many people are on the course and what kind of subjects you're going to specialize in, so that I can get you to investigate them on your own and come back and discuss them with us. The rest of the class, you can do that online or offline. We will play with videos or text, some way of you communicating what it is that you've learned, so that we can get a little bit further. But first of all, next time I will do a little bit more about coating in different ways, and maybe one other topic, and then we will distribute topics, decide on what themes you're going to do, and we'll go from there. So till next time.